Here I have given few questions from nuclear physics. The first question is, what is meant by phase shift? In a scattering problem, the scattering potential changes the phase of the radial wave function. The term phase shift measures the amount by which the phase of the incoming wave function is changed with a potential effect. Say a scattering potential is present here. If the particle is far away from the scatterer, it does not realize any force. When the particle comes closer to the scattering potential, then it may be deviated to some extent. The term phase shift measures the amount by which the phase of the incoming wave function is changed with the introduction of the scattering potential. The total scattering cross section is given by the formula 4 pi by k square summation over L equal to 0 to infinity 12 plus 1 sine square delta L. Here the term delta L is phase shift. If delta L is pi, that is 180 degree, then sine 180 is 0, so the total scattering cross section is 0. The area available for scattering is called cross section. Suppose the value of delta L is pi by 2, sine 90 is maximum, so the maximum area is available for scattering. Here L points out the orbital angular momentum quantum number. Suppose L equal to 0, which corresponds to the S wave. The low energy scattering is explained only with the help of S wave. If delta 0 equal to pi by 2, then sine square delta 0 equal to 1. Therefore, the total scattering cross section is 4 pi by k square. In this way, we should realize the concept phase shift. Then the second question is, what is meant by scattering length? In the case of low energy scattering, the scattering cross section is expressed by another formula, sigma S equal to 4 pi a square. Here A has the geometrical significance of radius of a hard sphere from which the neutron is scattered. With the help of scattering potential, we can construct a sphere of radius A. This is called the scattering length. The scattering length A is the intercept on the r-axis. R-axis means the distance of separation from the nucleus, and is obtained, that intercept is obtained by extrapolating the radial wave function. This is extrapolation of radial wave function. Inside the well, inside the square well, beyond the range R0 of the nuclear force. See this diagram. R0 is the radius of the nucleus. Suppose the particle is present inside the nucleus forces are dominating. If the particle wants to come out of the nucleus, it makes its to and fro motion continuously inside the squirrel potential. So that if you extrapolate the radial wave function inside the squirrel potential, the approach of the wave function is towards the direction of the squirrel potential. Beyond the range, which means that outside the squirrel potential, range R0 provides the radius of the nucleus. Beyond the range means outside the box. Beyond the range, the Coulombic potential alone be dominating, and if the particle is coming out of the Coulombic potential region, it is called as free particle. Now go through the definition once again. The scattering length A is the intercept on the r-axis and is obtained by extrapolating the radial wave function inside the well. This is inside the well. The direction of approach is towards the direction of the potential well. Beyond the range, outside the box, R0 is the radius of the nucleus. The distance is greater than the radius of the nucleus. We can get an intercept on the distance axis. That point of intersection is called scattering length. The scattering length is positive for a bound state and negative for the unbound state. Bound state means if if the nucleons are closer to each other and the nuclear forces are dominating. Suppose the distance of separation between the nucleons is more, that will be leading to unbound state. For unbound state, the scattering length is having negative value. For a bound state, the scattering length is having a positive value. And the third question is, what do you mean by nuclear parity? The parity operator is given by the formula pi equal to minus 1 power L. Here L is our orbital angular momentum quantum number. The nuclear parity tells us whether the wave function changes its sign or not on the inversion of coordinates. If the sign is not changed, the parity is even, and if changed, the parity is odd, which means that if psi of xy z is equal to psi of minus x minus y and minus z, the parity is even. Here this is an operator, parity operator. When it is allowed to operate on the wave function, the coordinates x, y, z are changed as minus x, minus y, minus z. This is called inversion of coordinates. Even though the coordinates are changed, but there is no change in the sign of the wave function, then the parity is even. See the second equation, pi into psi of x, y, z is equal to minus psi of minus x minus y minus z. On inversion of coordinates, the sign of the wave function is also changed in this case. Now the parity is odd. Then the wave function of this type is called symmetric. The wave function of the second type is called as antisymmetric. If the parity is even, such wave function is said to be symmetric. If the parity is odd, then the wave function is said to be antisymmetric.